Welcome to this video on further applications of right triangles. This would be after basic applications. These are kind of some niche applications. We're going to talk about two. We're going to talk about parallax or subtended angles, and after that, we're going to talk about that for a little bit. We're going to talk about bearing. Just two things here. Okay, so what we're talking about is for an object viewed at a distance, there is an angle that it subtends. Let me get my pen working. So a great example of this is the moon. Oops. Pen. If you've got you're looking up at the moon. Ooh, I know you love that drawing. You can measure the parallax angle, and typically you would measure the subtended angle as well, or the parallax angle, and know the distance. You could measure the width of the object, and vice versa. If you know the width of the object, some celestial body, you can find the distance. So, pretty exciting. We'll actually talk about a more accurate method for doing this without having to know that. Okay. Yes, so subtends bar method is one of the first ones we're going to talk about, and I actually used to do this, incidentally. I worked with a forestry company, and this was our cheap and easy way of gauging distances really quickly. So the idea is you've got some bar of known length. So I would carry a stick. I was always the guy to do the carrying. So you would carry a stick, and someone else would kind of look out at you and see what angle the ends of the stick made, because they know how long my stick was, my hiking stick, whatever. And with that angle, we can measure the distance. So, for example, find the distance when the distance d, and I've got a diagram of how we're going to do this. What we're going to do is we're going to take the length of our stick, or my walking stick, and divide it in half. And when I do that, I've got a right triangle. Actually, I've got two right triangles, but we only need one of them. So what you would do is you would measure the angle that the two ends of this stick made. You actually have to divide your angle in half here, because this is typically, you look according to this diagram, I'm measuring the entire angle. So I need to cut that in half, since I'm cutting this in half to make a right triangle. So let's see, find my distance when the angle there is 1 degree, 23 minutes, and 12 seconds. Well, first of all, I don't want to deal with minutes and seconds, so I'm going to convert that to decimal. I guess you don't really have to. So this is 1 plus, yikes, 23 over 60. So I divide the minutes by 60, and then the seconds, plus, I'm going to take my 12 seconds, and I have to divide them by 60 twice. Divide it by 60. And I'm just going to put another 60 right down there with it. Okay. So let me figure that out first, and I know I had a calculator. Let me pause this. I hope there's a pause button. There we go. Let me pause this and find my calculator. Okay, and I am back. So in order to calculate this, I need to do 23 divided by 60, and I get 0.383333333333. There we go. I'm not going to write all of that. In fact, I'm not going to write any of that on the. Yes, I will. I changed my mind. This is going to be 1 plus 0.383, and that second 3 is repeating. Oof, this pen program is not great. I can change the sign. Maybe this will help. Okay. All right, and then for 12, I'm going to divide it by 60 twice. And of course, you can do that in 2 steps or whatever you like. I'm entering it into my calculator all at once. Okay. You could also divide by, what, 3,600? 3,600 or 36,000. In any case, it's a really tiny number. 0.00333333. Just a bunch of threes. I'll stop running. So I need to add that to my 1 and add it to my 0.383. And I finally get my angle, 1.386 repeating. Yikes. Now, since my right triangle here, I only need half of that. I'm going to need to divide that by 2. Right, so this is my angle theta. I just converted it to a decimal, so it's easier to work with. Now I need to divide it by 2. I get a very tiny angle. Oops. 0.693 repeating. Now that we have that angle, this is what our triangle is. My poor attempt at a right triangle. So I've got my angle, theta over 2, 0.693. I also have the end, I know this short leg of the triangle. If my entire stick here is, my entire side here is B equal to 2 meters, well, half of that would be, this little part is going to be 1 meter. So that's the length of this side of my triangle. So the question asked for, they asked for D. We don't know D, but I know a trig function that will relate this 0.693 to the side we know and the side D. So that's the opposite side and the adjacent side. So if I have tangent of theta is equal to our opposite side over D, I need to solve this for D, so I'll need to multiply both sides by D. Did I write over here? No. It's 1 over D. So what I'm going to do, I multiply both sides by D. Not nearly as nice as I hoped. And that eliminates the D from the denominator on the right side. Now I would just divide by tangent on both sides, and I get D equals 1 divided by the tangent of our angle. I guess in our case, really should be tangent over 2. So using that formula and the tiny bit of space I have left, you know what? No, I can just erase. Neat. So this is a new program for me. That was fun. So now I can solve my formula here by plugging in the angle. My distance is 1 divided by the tangent of 0.69333. Remember that 3 was repeating. I just let that mark off. Excuse me. So 1 divided by tangent of that angle. I get the distance is 82.6. We're working with meters. Meters. There we go. Whew, that was fun. Now, for the next example, this is a more, you may want to pause and digest that for a second. This is a little bit more realistic of a scenario. This first example relies on you being able to figure out that angle. And that's kind of a hard thing to measure precisely. Uh, if you've got a really long stick, if our B here was like 10 meters, that would be a bigger angle, but still not going to be easy to measure. What do we do? Typically, you use stadium marks of some kind. So have I used this word stadia yet? No, that's a new term for us. This is kind of a method of stadiometric range finding, what we just did above. But anyway, using stadium marks on some kind of lens, a telescope or like a rifle scope, that's an example of a stadium mark. So what that is since you know how far, like you're looking in your binoculars, the stadium marks are in a set place because they know your eye is going to be right up against the like the scope you're looking in. They're going to have marks on it some distance, like maybe 5 inches away. So if they know the angle that they want you to be looking at, they'll just make that length. So whatever the angle that you're seeing on this mark is equal to the angle that you'll need to measure distance. So let me explain this a little better with this example and with a little bit of a diagram. So when we do this, say determine the angle necessary for placement of stadium marks. So we're going to first find the angle that we want, and then we'll talk about how you set up a stadium mark for that. So in our example, we're making a lens, and we want to know where or what angle our stadium mark should be at, so that a 6-foot object would appear in our scope. It would subtend that angle at 100 yards. So yes, less talking and more drawing, huh? It's very, just pretty much the same diagram we had before. That should be going right between those, and it is not. Ooh, that's tough to draw that long line. I feel like it'd be nice if this thing had a line tool. Yikes. Okay, so what we have here is we want to be able to look at something that's about 6 feet tall. So let's say use a little person here at 6 feet. He's very confused. And let's say also, why not we say he's holding a stick that's also 6 feet. You could do this with, if there's a 6 foot tall person or a surveyor holding a 6 foot tall stick. Either way, we've got 6 feet. We know that this is 6 feet tall. We want our distance to be 100 yards. So our question is, what angle should we be using here? And honestly, I don't even care. We're going to just look at the half angle. We're going to say we're going to find that angle. You could double it if you wanted. We're just going to find that one angle. But it's easy enough to do. This entire guy holding his stick is 6 feet. This would be 3 feet, right? Half of that distance would be 3 feet. Since we're working with feet in one part and yards in the other, we should probably convert that. So fortunately for us, this is pretty easy to do. 6 feet is 2 yards. And then 3 feet is what? 3 divided by 3 is 1 yard. We're just going to erase this. Do a little calculation elsewhere. Where's my pen? So yeah, we just want to convert. We want the same units everywhere. So 6 feet equals 6 divided by 3 yards. 2 yards. This guy is 2 yards tall, meaning this half of him is 1 yard tall. And now we've got the same units everywhere. Now we can finally deal with it. How do I relate this angle that I want to know to the opposite side and the adjacent side? Well, that sounds familiar. That's going to be our tangent. The tangent of our unknown angle, theta, is the opposite side 1 divided by the adjacent side 100. And then how would we find our angle? Well, we would use the inverse tangent function. So what we've done here, we take the inverse tangent of both sides. And it cancels out. It gets rid of the tangent on the left. Anyway, I can plug that in my calculator. All right, and I get 0.57, very tiny angle. Say 0.573 degrees. Although, in honesty, if we were manufacturing a telescope, we would probably have a little bit more precision than that. So that was the answer we were looking for. Now, what would we use that for? Back to our example. We're going to have like our telescope here, right, that you're looking through. They know your eye is going to be right here. Draw a goofy looking guy. He's very happy to be looking in his rangefinder. So they know where your eye is and they know the angle. What they would do is put in a stadium mark somewhere in here, like right there. So whenever this guy at the end is completely covered by that stadium mark, then you would know that he was standing 100 yards away. It's pretty neat. If you've ever used binoculars or something, or I know rifle scopes are pretty common in Mississippi. For those of you who are actually in Mississippi, you've got these little tick marks on your rifle. That's what they are. They're stadium marks, so that at a set distance, at a set distance, a person of a certain height would be covered by that. So pretty neat. So just a fun fact. Yeah. While we're at it, I'm not going to do any math for these, but some other ways this was done would be a coincidence or a stereoscopic device. I looked up a bunch of pictures of these. I just took them off Wikipedia. So this is nice because you don't have to have someone standing at the end of this thing. You don't have to know how tall they are or any of that stuff. What you do is you keep the stick from your subtended bar method. You keep it with you. You have this bizarre device using mirrors, and from this you actually can, as long as you make sure you have a 90-degree angle, so you're viewing this through this left side here at a 90-degree angle, then the machine would calculate this for you. It would find the angle, and from that you would either consult a table or be written on the machine itself. You would know the distance. Sorry, I'm always interested in this stuff, so I'll give you more information than you want. You're not going to be tested on this, so feel free to skip to the next part. The way it works is it focuses like any other pair of binoculars, and it won't actually come into focus until this angle is until you've got your your targeting solution, until you've got your 90-degree right triangle made by this. You can actually do it with the law of cosines or the law of sines, we talk about much later. And then you don't have to have a 90-degree angle. But this is a simple. So these were used a while ago, like the 40s era, and later. Well, I guess this is the battleship, the USS Alabama, I believe. It's in Alabama, down in Mobile. And I went there. I've been there a few times. I went there when I was a Cub Scout to spend the night, and my stepson went there to spend the night. I took him there, and I didn't remember any of this from when I went, but they've got one of these stadiometric rangefinders down here, and it's just massive. I mean, you can see the little person here. You can see this guy standing next to it. So he's about, I don't know, 5, 6 feet tall. And you could lay down a bunch of him between ends of this 5, 10, 15, 20, 25. That's at least 25 feet there between the ends of this. That allows you to get a pretty precise measurement. Oh no, I don't have my pictures in the machine. Oh well. This is super important on a battleship, and they actually have another one up here. Got another, like a backup one. I believe this would be like an electronic version, and this is the old school, like visual one. And it's super cool. They let you go in there and play with it. You can see the little tick marks on it. I need to go back and get a better picture of that. Anyway, I won't bore you anymore about this. It is really exciting. This particular battleship has a massive, like, full deck devoted to their old mechanical computers, because finding this distance without being able to do this, you could not find your firing solutions. They couldn't using these guns. Uh, but that's a longer story, and that actually requires differential equations to understand. We'll save that for another day. Oh, so I have to hold this thing at a kind of a weird angle so I can draw on it. Okay. So we're going to be looking at some bearing, used for navigation, surveying, etc., to indicate direction. Yeah. So there are two ways that these are done. The way you'll be presented with a bearing. If someone says bearing, 32 degrees, this is what they mean. They're saying starting from north and going counterclockwise or clockwise. um, that's the angle that you go through. Okay, that one's super common. If you use a compass, you're taking bearings to actually navigate. Typically, you're just going to be using that single method. More advanced navigation, people will want to know. They want to be able to fine tune this and do it quicker. They'll reference a particular cardinal direction, either north or south, and then say which direction they're going in. I should have rearranged these. So like this one, for example, north 42 east is north, starting from north and sweeping out towards the east. Hopefully you all know your direction. North, south, west, east. So if we're going north towards the east, we're going this direction. If we're going north towards west, we're going this direction. And that would be this other example. North 52 west means we're going to the west. Similarly, you can start from the south direction and go east, or the south direction and go west. So this textbook talks a lot about that. The examples that we're going to use to talk about this are kind of, what's the word, sneaky? They are not very realistic. Typically, with a problem like this, you would need trig functions that work for things other than right triangles. 90-degree angle. That's something that revolves around the law of sines and cosine and will be done at the end of this class. Okay. This one's a little cheeky because they just happen to pick a ship that ends up sailing at 90-degree angles. So a ship leaves port and sails on a bearing of north 47 east. So north east, and he is going at 47 degrees. So this angle here is 47 degrees. He goes for 3.5 hours, which I imagine we'll need. It then turns on a bearing of south 43 east. So let me draw this a little bigger. So from here, we're going to be going in the southern direction towards east. There's south and there's east. So if we're starting from south and swinging out to the east, we're going at some angle like this. Yeah? And that angle is 43 degrees. 43. And he goes there for 4 hours. Now let me make this a little simpler. I want to look at just a couple of things. I have one north-south line, and I have another north-south line. Those are the two, the same ones I have drawn over here. I've got this north-south line and this north-south line. Okay? Those are parallel because they're both running north and south. Right? You with me so far? Here's the sneaky part of this. I'm going to draw in the first ships. Ooh. I don't know what happened there. The first ships, so the ship's first path, excuse me, this angle is 47 degrees. Now, if you remember your geometry, since these are parallel north-south lines, this is also 47 degrees. And that's the only thing hard to recognize in these problems. You have to think, when you're looking at these cardinal directions, north, south, west, east, whatever, they're always going to be parallel lines. You can make these parallel lines and apply your old geometry rules. What are these, alternate interior angles or some silly name? But anyway, they're 47 degrees each. So I'm going to go back to our old picture here. I'm drawing a lot less. So rather than writing the 47 degrees in the bottom left, I'm only interested in this 47 degrees. Because with that, remember this one, the second direction this ship went, he was going in a southeasterly direction, an angle of 43 degrees. So this is where this gets cheeky. What's 47 plus 43? It's 90. So what they've done here is they've snuck in a right triangle. Again, not very realistic. Well, it doesn't really look like a right triangle. Can I erase this without erasing the whole thing? Yes. So now we've got a right triangle. And then the last question, what is the distance from the that the ship is from port? That would be, he started from the port. This is what they're looking for. What did they give us? They should have given us these distances. Did they? They said this guy was going 22 knots for 3.5 hours initially. So distance is equal to rate times time. You're going 60 miles an hour for 2 hours. You've gone 120 miles an hour. You just multiply the two. So in our first case, we've got this first distance is 22 knots times 3.5 hours. Punch that in the old calculator. And I get a distance of 77 miles, nautical miles. Because a knot is a nautical mile. Oh, I actually used to remember. I used to know this. I believe a knot is the distance on the surface of the Earth it would take in order to traverse like a single minute from the Earth's core. You want to go an angle of like a minute, maybe less than that, maybe a single second. It would whatever the distance on the surface of the Earth would be, that would be a knot. I can't remember that. It's been years since I looked that up. Okay, the other side we were going 4 hours for 22 at 22 knots. So again, our rate is 22 times 4 hours is going to be 88. So now we've got the two sides of our triangle. We can find the last one. Since it's a right triangle, you know, we can use the Pythagorean theorem, where our c here is equal to the square root of a squared plus b squared. So let me punch that all in the calculator. Square root of 77 squared, 88 squared. And I get that that is 116. 116.9. I guess we could round that to 117, but we're not going to. Who cares? I will never count off for minor rounding issues. It's just not that big a deal. I'm more interested in you getting the concepts here. So there we go. Lots of talking, not that many problems. Hopefully it shouldn't be too bad. I did want to go back up here. This was from a previous unit, section 1.1. And this is a surveyor's map from like the county records office. You can go look at any of these. I'm sure if your clerks are like the ones here in my town, they're really bored and they would love to talk about maps with you. Anyway, so you see these are typically given these are given not only in degrees, minutes, and seconds, but they're using that notation north and the angles swung out in the westerly direction. Makes sense. Going north, you've swung out just a little bit in the westerly direction. We should get a line. Well, we get that line. I wish this thing had a line tool. All right, but that's it. This was just more chatting. You know how I like to ramble. So if you made it this far, as usual, thank you so much. And I'll see you next time.